Oh,
Just thank you. Thanks. Hi, Peter.
Hey.
Peter Paul.
Yeah, exactly on time. It's my so first, for all the people attending on Zoom, you're very welcome to ask questions during and after the talk. Please just raise your hand and I will promote you and you can ask the question directly to the speaker. So today it's my pleasure to introduce Eleanor March. Eleanor is a PhD student at the Department of Logic and Philosophy of Science at the University of California, Irvine. She's published widely in philosophy of physics, including philosophy of spacetime and quantum mechanics. She got her undergrad degree titled MPhil from Oxford, followed by her master's degree called BPhil from Oxford. So someone should talk to Oxford about their naming convention. But today she'll tell us about minimal coupling, the strong equivalence principle, and the adaptation of matter to space-time geometry. Eleanor, floor is yours.
Thank you so much, Siddharth. Okay, brilliant. So, sorry, my slides weren't changing for a moment, but okay, that's just working. Good. So I want to begin this talk with two questions. Really, it will be three questions, as you see. The slide name was originally two questions, and I realized there were three, so I was like, it's changing. And the first question is a question that Jim began his talk with last week. So, what does it mean for the dynamics of matter fields and general relativity to be locally approximately special relativistic? And so we heard some things from Jim last time about what answers to this question might look like. The second question is also about properties that the dynamics of matter fields and general relativity might have. And I think was also suggested in some of the discussion last time. And the second question is, what does it mean for the dynamics of matter fields in general relativity to be adapted to space-time geometry? Okay, good. And so the way I wanted to begin this talk was by posing for you the question, what is the relationship between questions 1 and 2? What's the relationship, in other words, between matter dynamics, which are locally approximately special relativistic, and matter dynamics, which are adapted to space-time geometry in some sense? Okay. And I take it that there's, if you like, a sort of standard story that's maybe sort of implicit, or behind a lot of people have in their minds when they might think about what the answer to this question is. Sort of was gestured out again in some of the discussion during Jim's talk. And it goes something like this. So I've put up for you on the slides a few principles that we might think about when we're talking about properties of matter dynamics, or we're thinking about building matter dynamics in general relativity. So we have the principle of minimal coupling, we have the strong equivalence principle, we have a sort of local symmetry principle, which says that matter dynamics should be sort of locally approximately Poincare invariant. And I sort of take it that the standard story about the relationship between matter dynamics, which are locally special relativistic, and matter dynamics, which are adapted to space-time geometry, goes a bit like this. These principles, so minimal coupling, the strong equivalence principle, etc., are often taken to capture senses in which the dynamics of matter fields and general relativity are locally special relativistic, or locally approximately special relativistic. Good. But they're also taken to be relevant to the question when the dynamics of matter fields will be adapted to space-time geometry, when those matter field dynamics will be sort of well behaved in a suitable sense. And in what sense, you might ask? So I think the answer to this is sort of supposed to be something like principles like minimal coupling or the strong equivalence principle are supposed to be like candidate sufficient conditions or heuristics for building matter dynamics, which are adapted to space-time geometry in the sense that they exhibit features like the following. So we have motion, this principle I call motion, which you might think of in terms of the geodesic principle. So if my matter dynamics admit suitable small body limits, then in those small body limits, those solutions will follow only time-like or null geodesics sort of arbitrarily closely. I have a sort of principle of causality, which says my solutions don't propagate superluminally. They don't propagate outside the metric light cones. And I have a principle which says if I have a sort of candidate clock-like solution, so a solution which is sort of confined to some neighborhood or some curve and is sort of appropriately periodic, then in some suitable limits, it will measure arc length along that curve arbitrarily closely. Okay, good. So the theme for this talk is going to be, can we say anything more about this, more than this, about the relationship between locally special relativistic matter dynamics and matter dynamics which are adapted to space-time geometry. So you'll notice that when I put this up on the board, I said, oh, okay, there's something like candidate sufficient conditions or heuristics for building matter fields which have these features. It would be nice to be able to say something stronger. It would be nice to be able to say, if I have a matter theory which is locally special relativistic in the sense that it's minimally coupled, or satisfies the strong equivalence principle or whatever, maybe satisfies some further additional conditions, then that matter field theory will necessarily satisfy principles like motion, causality, and time. Okay, and at the moment, or sort of as it stands, as the way I want to sort of set this talk up is that the way that principles like minimal coupling and the strong equivalence principle are usually explicated, the answer to that question is we can't say anything more. The relationship is going to remain mostly heuristic. I don't really want to dwell on this for a very long time because I'd like this talk to be a bit more constructive. But the reason for this, I think, is related to something Jim was talking about last week, and that's because principles like minimal coupling or the strong equivalence principle are usually explicated syntactically. And this has the consequence that they're ambiguous. I don't think this is a sort of controversial point. The fact that sort of minimal coupling, for example, is ambiguous has been a sort of well-known theme in sort of textbook treatments of general relativity since, it's in Troutman's lecture notes, it's in sort of Misner's and Wheeler's classic discussion of it. If you understand minimal coupling in terms of the common goes to semicolon rule, then if you give me some special relativistic matter dynamics, there are sort of multiple distinct sets of general relativistic matter dynamics which sort of count as minimally coupled versions of those special relativistic matter dynamics. And so until we have a sufficiently clear or precise statement of something like minimal coupling or the strong equivalence principle, then we can't say anything more about whether these principles imply conditions like motion, causality, or time. Okay, so the aim for today's talk is basically to plug those gaps. So I'm going to do two things. The first thing is I'm going to try and provide for you precise statements of minimal coupling and the strong equivalence principle. They'll turn out to be closely related to the Euler style criteria that Jim discussed last week, which for those of you who were there. And then I'm going to sort of go some way towards plugging the gap between those conditions stated precisely and the sort of conditions that I said adaptive dynamics will have. In particular, I'm going to state and motivate for you some theorems which make clear the relationship between principles like minimal coupling and the strong equivalence principle, and the conditions I call motion, so the geodesic principle, and the principle of local causality. Okay, good. So yeah, just a brief outline of how that will go. I've done some background. I'm going to spend probably the majority of this talk introducing for you a particular class of theories of interest, theories which are minimally coupled, quasilinear, and symmetric hyperbolic. To do that, I'm going to begin by talking about a particular class of theories, which Jim and I have discussed. So natural theories, which is sort of one way of explicating what a sort of generally covariant field theory is supposed to be. I'll show how this notion of natural theories can be used to articulate what it is for a system of matter dynamics, so a system of partial differential equations, to depend on some background structure to some order. And this will allow us to articulate the criterion of minimal coupling. It will also allow us to articulate the strong equivalence principle, and I'll say a little bit about what the relationship between minimal coupling and the SEP is supposed to be. And then I will move on. I will state for you some results about properties that minimally coupled symmetric hyperbolic theories have, and use those to answer the questions that we began with. Okay, excellent. So, I'm going to begin by talking very generally about what a matter theory is. And in particular, I'm going to assume that a matter theory is given by a system of partial differential equations on some space-time manifold that I'm interested in. Okay. Clearly, in order to make progress with that definition, I'm going to need to say something about what an equation is. And in particular, I'm going to want to do this in a way that's suitably non-syntactic. So that's going to avoid the kind of ambiguity worries that I was mentioning with minimal coupling in the sort of introduction of this talk. Okay, so very roughly, the way that we're going to do this is as follows. I'm going to have some smooth n manifold. That's going to be my sort of space-time that I'm interested in. Any system of kth order partial differential equations on that manifold is going to be associated uniquely with a suitable closed embedded submanifold E of a certain fiber bundle over that manifold M. And in particular, we're going to think of the points in the fibers of that bundle. We're going to set things up in a way such that we can think of the points in the fibers of that bundle as tuples consisting of possible field values and their partial derivatives up to the order of the equation k at that point. And so this submanifold can be thought of as the space of tuples of field values and their derivatives up some order, which solve the equation at each point in the manifold. Okay, and conversely, if you begin by giving me an equation which you've expressed in some suitable region, in some suitable coordinate system, syntactically, so in terms of a sort of particular expression relating field values and their partial derivatives, then I'm going to be able to get an equation from that and also go in the other direction. So if I fix local fibered coordinates on this bundle, I'm going to get back a syntactic expression for an equation that's sort of probably more familiar. Okay, let me just say how that works in a bit more detail. So we're going to consider a smooth fiber bundle over M, B. B is going to be, if you like, our space of possible field values at each point in the manifold. And recall that a smooth section or a smooth local section of the fiber bundle is a map from some region O of M to B, which takes points in O to points in the fiber over that point. Okay. Any such fiber bundle is going to give rise to a family of jet bundles for each natural number k. And the fibers of those jet bundles consist of the spaces of all k jets of those local sections of my bundle B. Okay, and so the k jets of my local sections of B can be thought of as B fields and their partial derivatives up to order. Okay, good. And a kth order partial differential equation on that fiber bundle B is then going to be a closed embedded submanifold of that jet bundle. And a solution is going to be a section of my bundle whose kth jet prolongation lies within my closed embedded submanifold B. Okay, good. Just to kind of make this explicit how this works, so running example is going to be Maxwell's equations throughout. So if we start with the bundle, if I have a space-time manifold M, GAB is a Lorentzian metric on M, and I have the bundle of two forms on that manifold, then I can define a particular vector subbundle of the first jet bundle of this bundle of two forms. And it just consists of all the points which expressed relative to, which satisfy Maxwell's equations expressed relative to the metric G that I fixed on that manifold and its associated Levi-Civita connection in the way that you normally would. Okay, good. So, that was a very general spiel about what a matter theory might be in general. And what an equation might be in general, but in physics, we're generally not interested in any old equation on any old bundle. And one particular class of equations that we might be interested in are those which are generally covariant in something like the Kretschmannian sense. By saying Kretschmannian, I don't mean to take a sense on whether it's trivial. What I mean is they're generally covariant in the sense that Kretschmann famously claimed was trivial, but turns out actually not to be trivial. Okay, but in any case, what does this notion of general covariance amount to? Roughly, there are sort of three things that it should require. So the first thing is, given any smooth M manifold, I can always construct my bundle of field values and equations thereon. So the idea here is, you give me any smooth M manifold, I can tell you what my space of possible field values is like on that manifold, and I can tell you what the equation looks like on that manifold. So think about Einstein's equation. I know how to write down Einstein's equation on any manifold I like. I don't need to restrict to a particular manifold, I can just do it on any manifold. Secondly, if I have a smooth embedding or a diffeomorphism between two of these manifolds, then this is going to lift uniquely to a smooth bundle morphism between these bundles of field values. So the idea here is, if I want to say that my equation or my dynamics are in some sense invariant under diffeomorphisms, then I first need to be able to say, okay, I know what it is for a diffeomorphism to act on my space of field values. So this is going to require that if you give me a diffeomorphism, or more generally a smooth embedding between two N manifolds, and I have my bundles of field values on those manifolds, then that diffeomorphism is going to have a unique privileged lift to act on those spaces of field values. And finally, you want to say that the equation is going to be preserved under those lifts of diffeomorphisms to the space of field values, or more generally smooth embeddings. Okay. Good. So how can we make these conditions 1 to 3 precise? So here's how it goes. I'm going to start with the category, which I'm calling M, whose objects are smooth M manifolds, and whose arrows are smooth embeddings between those manifolds. And I'm going to consider the category whose objects are smooth fiber bundles and whose arrows are smooth bundle morphisms. Okay.
Excuse me. I just want to, can I just step back and just make sure I understand the order of presentation? So you have a base space-time, a base space. You have a fiber bundle that's associated with each point on that base space. Then in a fiber bundle and the base space, you can add a twist in some cases. And is there a twist here? That's question one. Second, I take it the reason that you're setting this up is that you want to present the differential equations as a geometrical object that will be then located or associated with this. And the closedness is to include the limit points on the base space plus fiber bundle plus maybe or maybe not a twist. Have I got the basic, like just the crude layout of what you're doing?
Yeah. So okay, whether or not the fiber bundle is, if you like, twisted in some sense, I'm sort of remaining neutral on. It may or may not be. It might have a trivial topology. It might have a more interesting global topology. None of this will depend on those kind of global topological issues.
Okay.
Yeah, so that's exactly right. So the idea is, you want to think of an equation as a particular submanifold of some fiber bundle, and the closedness of the equation as a submanifold of that fiber bundle is basically capturing the idea that it's an equation, not an inequality. So if I wanted to be more more general and talk about differential inequalities rather than equations, I could drop the closedness condition. But I'm specifically interested here in differential equations. Does that kind of help?
So the differential equation is going to be thought of as a geometrical object in this more complicated submanifold, right? Is that why we're doing? Is that why we've gone back? So we want to be able to do differential geometry on this, and so we want the whole thing to be geometrically represented. Is that the? I'm just trying
Yes,
to get a like big picture of what you're
yeah,
doing.
so we'd like the whole equation to be geometrically represented. And in particular, the whole equation is going to be represented by a sub-manifold of this bundle that we're interested in. So in that sense, it's a geometrical object. Does that help?
Okay.
Okay. Okay, good. So back to general covariance. We're going to define a particular class of bundles that we're interested in. These are going to be the bundles, the sort of bundles which you construct over every n manifold, and they're the sort of bundles that diffeomorphisms or smooth embeddings between n manifolds lift uniquely to bundle morphisms. These are called natural bundles. How do we define this? We're going to define a natural bundle as a functor from the category of n manifolds to the category of fiber bundles, which has the following two properties. It associates to each manifold a fiber bundle whose base space is that manifold, and it associates to each smooth embedding between n manifolds a smooth bundle morphism which covers that smooth embedding on the base spaces. Okay, good. Just some examples of this. So that sort of was a very abstract definition, but this is very familiar, this idea. So tangent bundles are an example of this. So given any smooth n manifold, I can always construct as tangent bundles. And if you give me a smooth embedding between two n manifolds, then this will determine a unique smooth bundle morphism between the tangent bundles to those manifolds via the push-forward construction. Similar point goes to for frame bundles, bundles of M forms for some fixed M, bundles of affine connections, bundles of Lorentzian metrics, and so on and so forth. Okay, good. There are a couple of useful observations to make at this point. First observation to make is that if I have a natural bundle.
Eleanor, just a quick question. So what was I sort of missed what the naturalness is. So what is the key naturalness claim?
So the key
like
naturalness
what
claim
and why are we calling it natural is basically my question.
I mean, in some sense, it's just terminology and it's been around in the math literature for a while. But I mean, the idea is just that the construction of this particular class of bundles from manifolds is functorial, and in that sense is natural. So the idea is that these bundles, if you like, so think about the tangent bundle, like they depend only on the structure of their base space. So if I have a manifold and I construct its tangent bundle, then I can figure out what properties that tangent bundle is going to have just by thinking about properties of that manifold. Does that kind of make sense?
Maybe a little bit. So this is not terminology you're introducing, this is standard terminology, and the thought is, I mean, usually when I hear the word natural, I assume there's like it's the most natural thing you can do, like it's the most obvious thing you can do. And is there some sense in which this is the most obvious thing you can do with this?
I think this is a use of natural. I mean, so natural has like two senses in which it's used, right? So there's the natural in the most obvious sense, and then there's also sort of the natural in the kind of functorial way. And this is kind of natural in the sense of being functorial. Does that, yeah. But, I mean, you could just think of it as terminology.
Okay. But okay, maybe another way to ask the question is like physically, what are we trying to sort of point at with this?
So the idea is we want to construct bundles which represent spaces of possible field values that have the following property. If you, I can say what it is to act on those field values with a diffeomorphism or a smooth embedding in a way that's well defined, which I'm going to need if I want to say, okay, my equation or my dynamics are going to be preserved under smooth embeddings or diffeomorphisms, which is sort of one way of thinking about what general covariance means.
Okay, that's helpful. Thank you.
Okay. Good. So, there's sort of two observations to make at this point. The first observation is if I have a natural bundle, then its kth jet bundle is also going to be natural. So there's a sort of formal way to see this, and there's an informal way to see this. The basic point is just that the jet bundle functor is in fact a functor from the category of fiber bundles to itself. And the second point to notice is that the collection of all natural bundles over n manifolds also has the structure of a category whose arrows are natural transformations between those natural bundles. This is actually all the setup we need to define a natural equation or a generally covariant field theory. So what I'm going to say is a kth order natural equation or a kth order generally covariant field theory on some natural bundle X is going to be a sub-object of this kth jet bundle of X in the category of natural bundles. That's a very abstract definition, so let me just like gloss it for you. The idea is a kth order natural equation on a natural bundle should associate to each manifold a particular closed embedded submanifold of the kth jet bundle of X at that manifold. It should make that association in a way that's also functorial over manifolds. And it should do that in such a way that these like distinguished submanifolds that are sort of my spaces of point-wise solutions to the equations are going to be preserved under the lift of smooth embeddings between these n manifolds. This is just what this definition states. And so in that sense, it just realizes the points 1 to 3 that I said were sort of what you should want a generally covariant field theory to do for you. Okay. Good. So I just gave you a definition of a generally covariant field theory or a natural theory. You might ask, given this definition, are standard examples of field theories considered in physics natural? In general, the answer to this question is going to be no. And this is because field theories in physics are often formulated relative to a sometimes implicit choice of background structure. So just to kind of make this vivid, consider the Maxwell system that I presented for you earlier. So if I have a bundle of two forms, that's a natural bundle. Given any diffeomorphism from some manifold M to itself, it's going to just determine a smooth bundle isomorphism on the first jet bundle of the bundle of two forms over that manifold. Okay, but Maxwell's equations formulated relative to a fixed background Lorentzian metric in the way that I presented them earlier are not going to be preserved under these isomorphisms. In fact, the equation submanifold E of the jet bundle J1F is going to be preserved just in case that diffeomorphism fixes the metric, just in case it's an automorphism of that Lorentzian manifold. Okay, and so the Maxwell system can't be natural, because if it were natural, E would have to be preserved on the lift of arbitrary diffeomorphisms, and that's not going to be the case in general. Okay, good. You might think, okay, fine, whatever. But there's something a little bit weird about this, which is that you might think, well, okay, but the Maxwell system would be natural, it would be generally covariant if we were to make the dependence on the metric explicit. So what you did was fix the Lorentzian manifold and then think about Maxwell's equations as equations on spaces of two forms on that manifold. But if you were to sort of make precise the way that the metric also features in those equations, then it would be generally covariant. Okay, that is, so the equation might not coincide with itself under the lift of some arbitrary diffeomorphism, but it will coincide with the equation that you'd get by expressing Maxwell's equations relative to the push forward of that metric by that diffeomorphism. Okay, so we would like to be able to make this idea precise. Okay, here's how we do it. We're going to start with a natural bundle X, and I'm going to define a particular kind of bundle, a natural quotient bundle. That's the abstract definition. I'm not actually gonna read it to you. Formally, it's a quotient object in the category of natural bundles, which makes it into a smooth fiber bundle. But the rough idea is just the following. a natural quotient bundle of X is going to insert a fiber bundle Y M between each X evaluated at each object M. So for each n manifolds, I'm going to have a bundle XM, and I'm going to specify a choice of fiber bundle YM at each M, which is going to build a fiber bundle either side of YM. So XM is going to be a fiber bundle over YM, and YM is going to be a fiber bundle of M. And I'm going to do this in such a way that everything is functorial, everything's going to be preserved, all those relationships are going to be preserved under the lift of smoothing beddings to X and Y. Okay. The way you should think about this is what we're going to want to do is we're going to want to think of this bundle X as a bundle of sort of matter field values plus background fields. And we're going to want to think about this bundle Y as a bundle just of background fields. And so I have these natural transformations, which are given by these lowercase y's, which tell me how to think of the space of field values that I'm interested in plus background fields as living over just the space of background fields. Okay, good. This has the following consequence. If I'm given a natural quotient bundle and you give me your favorite n manifold and your favorite section of my bundle Y of background fields, then I can construct a new bundle, which is just going to be the pullback of the bundle XM over YM by this section of Y. Okay. Good. The idea here is, so if I have my bundle X, which I said you should think about as a space of physical fields that I'm interested in, plus background fields, then I make a particular choice of background structure. Then what I can do is I can think about the space of physical fields that I was interested in relative to that choice of background structure. So I can restrict this bundle to the points in the bundle that lie over this section, which represents my particular choice of background structure, i.e. a section of the bundle Y. Okay, and this is going to allow us to articulate the idea that we had with the Maxwell example earlier. So the idea here is we're going to define a particular thing called the naturalization of an equation. How we're going to define this? So a naturalization of an equation is going to consist of a natural equation, which gives rise to the equation that I started with relative to some choice of background structure. So how does this work? The idea is you give me your equation E, which isn't necessarily natural. A naturalization of this equation is going to be a natural equation on a natural quotient bundle, such that if I take the manifold that I was interested in, that I began with, and I make a particular choice of background structure, so I choose a particular section of my quotient bundle, and I restrict my natural equation on that manifold to that particular choice of background structure, then what I get back is just the equation that I started with. That is all that this definition says. Okay, good. Just to kind of say exactly how to work with the Maxwell example to kind of make this a bit more intuitive. So I can consider the bundle of Lorentzian metrics. That's a natural bundle. And I can consider a bundle which every manifold is the fiber product of the bundle of two forms with the bundle of Lorentzian metrics. So the fibers of the bundle are just pairs of two forms of Lorentzian metrics. There is a natural transformation which takes this bundle, which I call F cross G, to the bundle of Lorentzian metrics. It's just given by projection onto the second factor at every manifold. And this makes the bundle of Lorentzian metrics a natural quotient bundle of the bundle which has fibers which are pairs of two forms of Lorentzian metrics. Okay, good. So then what I can do is I can define a natural equation on this bundle F plus G. The way that I'm going to do this is very simple. Every point in the fiber of that bundle, there's going to be a Lorentzian metric at that point. I'm going to consider what Maxwell's equations look like expressed relative to the Lorentzian metrics. I'm going to consider all the two forms which satisfy Maxwell's equations for that value of the Lorentzian metric and its Levi-Civita connection. I'm going to do that for every choice of metric and Levi-Civita connection. And this will give me a natural system of equations. And this will be a naturalization of the Maxwell system that I started with, because if I make a particular choice of metric, then what I can do is I can pull back my bundle F cross G to that choice of metric. I'm going to get something that's canonically isomorphic to my bundle of two forms that I started with. And what's the equation going to look like? Well, it's just going to look like Maxwell's equations expressed relative to this particular choice of metric. Okay. Yes.
Maybe we can see, so if I understand correctly, so what you're saying is there's some way to write down Maxwell's equations where you don't have to have where there is no sort of where the dependence on the metric is kind of abstracted away from, and then if you want to sort of write down specific equations with respect to specific metrics, you can do that, right? So do we have a sense of what that sort of broader Maxwell's equation looks like? The more
yes, so the broader Maxwell's equation, I mean that's exactly right, right? So the broader Maxwell's equations, if you like, all that I've done in moving from the Maxwell's equations that I started with to this sort of broader version of Maxwell's equations is that I'm now like considering the metric as also being a physical field, and I can make choices as to what value that takes. And I'm just making that explicit because we already know how to write down Maxwell's equations relative to any Lorentzian metric we like, right?
So is it sort of, I mean, so just think about it more like a sort of physicists might think about it. So are we just like sort of taking the electromagnetic fields and the metric fields and then sort of having that whole coupled, I don't know how many differential equations, and that system is what we're sort of considering, right? Is that right?
Yeah, exactly. So in the way that I presented this particular example, they're not sort of like coupled in the sense that, for example, like the Einstein-Maxwell system is. So I haven't put any conditions on the metric, but I could get the Einstein-Maxwell system by sort of imposing some additional conditions on the metrics, namely that they satisfy Einstein's equation. Does that make sense?
I think so, yeah.
Okay. Good. Okay. I mean, the reason that we're doing all this is because we want to get to this point. So, once I have this notion of what it is to naturalize a system of equations on the table. So once I have a precise way of saying, this is how I make explicit background structure in my equations, and I make explicit what order it's appearing at, then I can say, okay, this is what it means for an equation to depend on that background structure. In particular, and I won't read out this definition for you, we can have the following definition of what it is for an equation to depend on some background structure. We can say an equation depends only on some background structure to some order if that background structure can be used to make the equation natural at that order. So if I can use some structure to naturalize a system of equations that wasn't already natural, and I can use it to naturalize that system of equations at some particular order, then I'm going to say that the equation depends only on that background structure to that order. Okay. So, for example, in the Maxwell case, we just saw I can construct a naturalization of the Maxwell system expressed relative to a fixed Lorentzian metric by having a background bundle of Lorentzian metrics and considering the first order system on the natural bundle of two forms and Lorentzian metrics. And so there's a precise sense in which I can say, okay, the Maxwell system depends only on the metric to at most first order. I'm saying only and at most first order because it might depend on less than this in general. So in general, you can sort of always chuck in some like superfluous background fields if you like that aren't doing any work. But this gives me a notion of it only depends on this stuff. It might depend on less. Okay. And this is exactly what we need to articulate the notion of minimal comfort. So I'm just gonna define a minimally coupled equation to be one which has the following property. So I'm going to say a minimally coupled system of natural equations.
Sorry, Eleanor, could you just remind us intuitively what minimal coupling is supposed to be before you tell us the mathematically precise way to say it?
Of course, yeah, good. So there's a few ways that minimal coupling is sort of thought of in the physics literature, right? There's like the comma goes to semicolon rule and so on and so forth. But the way that we're thinking about the sort of intuition behind minimal coupling is just that minimal coupling means depends only on the metric to first order. So I shouldn't have like higher order dependencies on the metric appearing in my minimally coupled equations. I think this is what sort of comma goes to semicolon rule was sort of intuitively supposed to capture, right? The idea being I'm not going to insert extra second order dependencies or extra curvature terms into my equation by hand when I like go from special relativity to general relativity. I'm just going to want the equations to depend only on the metric and its first partial derivatives. And the idea is now that I've articulated a precise notion of dependence on background structures of some order, I can now just make that intuition that the minimal coupling is just the same thing as depending on the metric to first order precise very easily because I've just given a precise definition of dependence. Does that help?
Yeah. Okay, that's helpful. Thank you.
Okay, good. So I'm going to define a minimally coupled equation as follows. And so the idea here is a minimally coupled equation is a natural equation on a natural bundle which has the bundle of Lorentzian metrics as a natural quotient that has the following property. If I have any two Lorentzian metrics which agree to first order at some point, then the equation spaces restricted to those Lorentzian metrics also agree at that point. So this makes precise the sense in which the denaturalized equations only depend on the metric to first order. And the only fields that the equations depend on, if I denaturalize them, are the metric. Does that make sense? There's like another way of thinking about this, which is a minimally coupled equation is one that gives rise to, is one that I can obtain by is a naturalization of a system of non-minimally coupled equations which depends only on the metric to first order. So if I have a Maxwell system expressed relative to some fixed Lorentzian metrics and I naturalize it in a way that it's naturalized over the bundle of Lorentzian metrics and the whole thing is first order, then that thing is going to be a minimally coupled system of equations. And I'm going to call this a minimal coupling of the system that I began with. So you can think of this as a precise way of saying, okay, when I think about minimal coupling as a prescription for or recipe for building general relativistic matter dynamics from special relativistic ones, then what I'm doing is I'm telling you how to generalize my matter dynamics from being expressed relative to a particular metric, in this case, a flat metric, to arbitrary Lorentzian metrics. And I'm telling you how to generalize it to arbitrary Lorentzian metrics in a way that doesn't depend on the second and higher derivatives of those metrics. And this is just the mathematically precise definition of that. Okay. There's a really nice fact about this result, these definitions, which is that if you understand minimal coupling this way, then in the cases where it's sort of defined, it provides a unique prescription for constructing general relativistic field equations from special relativistic ones. So you can think of this as sort of resolving the ambiguity worries that that have been raised in the literature about sort of the comma goes to semicolon rule or other textbook statements of minimal coupling. So if I have a not necessarily natural equation and I have a minimal coupling of it, then if that exists, it's the unique such minimal coupling. And the idea here is really, really simple. The idea here is just because any two Lorentzian metrics coincide to first order under some diffeomorphism at any point I like, I can just use these diffeomorphisms to push forward the equation to arbitrary Lorentzian metrics sort of point by point. And if the result of this is to define a consistent sort of smooth submanifold of the jet bundle of field values out over those at each point, then that's the only thing I can do. So I get a sort of unique way of generalizing field equations expressed relative to one metric or expressed relative to a flat metric or the Minkowski metric to arbitrary Lorentzian metrics in the cases where this makes sense. Okay.
Sorry, so you said that this addresses an ambiguity worry. Can you quickly tell us what the ambiguity worry was?
Yeah. So I gestured at this really early on in the introduction. So the worry is if you sort of open up a general relativity textbook and you look at the discussion of minimal coupling in there, you'll sort of probably find something a bit like the comma goes to semicolon rule. So and it's sort of been noted for a very long time. So there's discussion in Misner, Thorne, and Wheeler. There's discussion in Traum inflection notes about this. That the comma goes to semicolon rule is sort of ambiguous in the following sense. If I have a system of equations expressed relative to a flat metric, and I want to generalize this to arbitrary Lorentzian metrics, then I can sort of get multiple distinct systems of equations for sort of an arbitrary Lorentzian metric in the following way. I can sort of commute partial derivatives in my special relativistic version of the equation because it doesn't matter, because the metric is flat. And then I can do the comma goes to semicolon prescription. And then what's going to happen is that I'm going to get two distinct systems of equations because one of them will sort of pick up a curvature term relative to the other. And then it's not clear which of these is supposed to be the correct minimally coupled equation. And oftentimes, in fact, pretty much all the time, everyone has an intuition about which of these is the right one. And everyone seems to sort of agree on which is the right one. And there's like an obvious one that has nice properties and is like very well behaved, and the other one sort of has pathological properties. So if you think about Maxwell's equation, like one of the versions is like gauge invariant, and the other versions are all gauge dependent, for example. But there's no way of saying, okay, only one of these is the correct sort of minimally coupled equation, and the other ones are somehow not minimally coupled, even though so people have the intuition that all the other equations depend on curvature or have a sort of non-trivial curvature dependence. That's the ambiguity worry. And so the way that this resolves this is by saying, okay, in the cases where minimal coupling makes sense, which is the first order theories, and this is the only case where you could state it, there's this minimal coupling provides a unique prescription for building matter dynamics from relative to any Lorentzian metric, from matter dynamics expressed relative to some fixed Lorentzian metric. It resolves the worries about higher order equations in the following sense. If I have a higher order system of equations, I can usually reduce the system to first order. And once I have a first order system, then this uniqueness theorem applies to it. So any kind of ambiguities have got to be resolved at the level of identifying these first order systems. And in fact, what happens is with the Maxwell case is that there's one way of making the Maxwell system expressed in terms of the vector potential into a first order system, which omits a minimal coupling, and the other ways of doing it don't. We could maybe I could talk about this over email. It's going to be long to go through the example.
Only about 10 minutes left, so yeah, sorry.
Yeah. Okay. Good. Okay, I'm going to very briefly mention strong equivalence principle because Jim kind of previewed it last week and promised you that I talk about it. So here we go. The idea of the strong equivalence principle is actually very similar. So the intuition I take it behind the strong equivalence principle is something like this. What does the strong equivalence principle say? It says that at least at a point, my matter dynamics are, if you like, the same as the matter dynamics in flat space-time. So if I take my system of natural equations and I express it relative to a particular Lorentzian metric, and I express it relative to a flat Lorentzian metric, or indeed any other Lorentzian metric, given what I was saying earlier and what Sam discussed in his talk a few weeks ago now about that any two metrics coincide to first order. So express it relative to two different Lorentzian metrics, and I find some diffeomorphisms such that some local diffeomorphisms such that those two Lorentzian metrics agree at some point. Then those equations agree. So I can always think of my equation as sort of at a point the same as the same equation relative to any other Lorentzian metric. That's just what this definition says. So it says a natural equation satisfies the strong equivalence principle just in case, if I express my equation relative to a particular choice of background structure, a particular Lorentzian metric, and then I pick some other Lorentzian metric, and in particular, if I pick a flat Lorentzian metric and express it relative to that Lorentzian metric, then under those diffeomorphisms, which make the two metrics coincide at a point, the equations are also going to coincide. Okay. And this is sort of closely related to the Euler style criteria that Jim discussed last week. So the relationship is basically the following. You could think of this statement of the strong equivalence principle as a point-wise version of the Euler's criteria that holds exactly. So rather than holding approximately in some neighborhood, it holds exactly at a point. There are other things you can say about this, but maybe ask me at the end if we can. Okay. Okay, good. Here's a nice fact. A first order natural theory is going to be minimally coupled if and only if it satisfies the strong equivalence principle. Actually, there are things that you could say about this higher order, but I don't think we're going to have time for me to sketch what's going on there. But this is nice because lots of people have wondered sort of what the relationship is, especially in the philosophy of physics literature. People have wondered sort of what's the relationship between the strong equivalence principle and minimal coupling, and you've had claims that it's minimal coupling is necessary for the strong equivalence principle, or maybe it's sufficient for the strong equivalence principle. And it turns out that it's sort of equivalent under some sort of reasonableness, fairly reasonable additional assumptions at higher order. And in the first order case, they're exactly equivalent. Okay, good. Now we get to the punchlines. I'm gonna save for you 3 results because I have 5 minutes. So once you have this notion of a minimally coupled theory, we can now ask, okay, what nice properties do minimally coupled theories have? In fact, you can show that they have the following properties. So if I have a minimally coupled theory, which is quasilinear, I'm going to assume the notions of quasilinearity and also symmetric hyperbolicity, which are standard notions, but if you want to talk about them, ask me at the end. If I have a minimally coupled theory, which is quasilinear, and I express it relative to a particular Lorentzian metric, and the result is a system of equations which is symmetric hyperbolic. So, for example, Maxwell's equations have this character, so does the Klein-Gordon equation. Then this system of equations is going to satisfy a precise version of the principle of local causality, namely the sort of causal cones of my symmetric hyperbolic system are going to coincide with the metric light cones. And so there's sort of precise results to the fact that if I have a hyperbolic system and I have the cones of that hyperbolic system, and then those represent the maximal velocities at which solutions can propagate off a point. And this result says if I have a system which is symmetric hyperbolic and minimally coupled, then those causal cones of the hyperbolic system, which tell me where solutions can propagate, coincide with the metric light cones, which is great. It means this is sort of a precise way of saying if I have a system which is minimally coupled and hyperbolic, then it's not going to, solutions aren't going to propagate superluminally. It's actually a really short step from this result to the next result, which says if I have a system of equations which is minimally coupled and symmetric hyperbolic, then don't worry about the details, but it says that it can be associated with a rank 2 symmetric tensor field, which is non-vanishing only where the matter fields are and satisfies the dominant energy condition. That's very nice, and also satisfies the covariant conservation condition. Okay, so if you like, there's the 3 nice properties that minimally coupled hyperbolic field theories have. So sorry, just to kind of end the talk and say why you should care about these properties, I wanted to return to the questions I began with. So I began by asking, what's the relationship between locally special relativistic matter dynamics and matter dynamics that are adapted to space-time geometry, in the sense that they satisfy some version of the geodesic principle, that they're sort of don't propagate superluminally, maybe they satisfy the clock hypothesis. We can now say something really careful and precise about what this relationship is. So we know there's this lovely result due to James Owen Weatherall, which says if I have a system of equations and they can be associated with a rank 2 solutions of the system can be associated with a rank 2 symmetric tensor field, which is non-vanishing only where the matter fields are and satisfies the dominant energy condition and covariant conservation condition, then if this emits a suitable small body limit, in that small body limit, solutions of this equation will follow only null and time-like geodesics arbitrarily closely. So in that sense, the dominant energy condition and the covariant conservation condition imply this principal motion, they imply the geodesic principle in some sense. We also know that if I have a system of equations now, which is minimally coupled and symmetric hyperbolic, then it's going to be Gaussian and causal, it's going to satisfy this version of the principle of local causality, and it's going to satisfy the dominant energy condition, and it's going to be covariantly conserved. And we also know that minimal coupling is equivalent to the strong equivalence principle, which means, punchline, if I have a system of equations which is minimally coupled and symmetric hyperbolic, then it's going to satisfy these principles causality and motion. And similarly for the strong equivalence principle. And I have 1 minute to say this. This kind of gives you an answer to the question that Jim asked right at the end of his talk a couple of weeks ago, which is sort of what would go wrong if matter dynamics were to fail to be locally special relativistic, in the sense of the Euler style criteria, for example. And the answer is, his answer is nothing would go wrong. But in some sense, being locally specially relativistic, if you like, is sufficient for your matter dynamics to be adapted to space-time geometry in these senses. So you no longer have any guarantee that your matter dynamics were sort of well-behaved or adapted or well-adapted in the senses of causality and motion if criteria of being locally special relativistic, like SEP or the Euler style criteria from last week, were to fail. Okay. I think that's all. Thank you very much.
Okay, we have literally just 1 minute for Q&A. Maybe I'll allow 2 minutes. Any questions in the room? Oh, yeah. Jacob, go ahead.
Thank you. Can you hear me okay?
Yeah.
Yes.
Thank you, Eleanor. That was a really lovely talk. I really enjoyed it. So what I take this to be the statement is, if we talk about matter on general relativistic spacetime in terms of an appropriately generalized notion of classical field theory on curved spacetime backgrounds, we have clear, rigorous statements about things like the strong equivalence principle and minimal coupling, and then we can prove various uniqueness theorems and so forth, and that's all really excellent and wonderful. So I teach graduate general relativity occasionally here at Harvard. Of course, I talk about the equivalence principle, the strong equivalence principle, minimal coupling. And the way I usually phrase it is more generally than I think we see here, right? I don't specialize to matter theories that are expressible specifically as field theories on spacetime. When I introduce the strong equivalence principle, what I say is this. Remember from special relativity, the two basic principles are that the basic laws of physics are independent of one's inertial reference frame. And the second is that no signal carrying phenomenon can propagate according to any observer in an inertial reference frame faster than the speed of light, right? Those are the two basic conditions. And what I tell students is the strong equivalence principle is the statement that if you're in a free fall frame, if you are an observer moving along in general relativistic language, a geodesic of spacetime, then in infinitesimal neighborhoods, you will see these two principles satisfied. It doesn't matter what your inertial reference frame is, and you won't see signals propagating faster than light. Notice these don't make any reference to how we're formulating our matter theories, right? They're very general in principle, they would apply, of course, to classical field theories, but they also provide strong constraints on semi-classical physics. For example, if I begin to think about basic quantum effects, obviously I'm not going to do quantum gravity, but we do have sensible notions of how to handle systems with some degree of quantum mechanical effects. It could be quantum field theories in curved spacetime. It could be something even more simple, just systems of qubits that are being studied on a curved spacetime. We have a formalism for this, but it doesn't quite fit into this picture of classical field theory. So in a sense, it's a more general set of constraints. But the fact is, it is a very strong set of constraints. If I think in terms of somewhat more geometric language, what I'm saying is, yeah.
We're running low on time, so could you
Okay.
just ask a question and let Eleanor respond?
So I guess my question is there a way to take these results and generalize them in a way that is broader than just thinking about classical matter systems on spacetime? I want to be able to say something like if I have.
That's the question.
Yeah, sorry.
Eleanor, please.
Yes, that's it. That's my question.
Yeah, great question. I think that's a really interesting question. I think that's like the natural next thing to do with this project. Now that we have like a nice handle on what kind of versions of sort of the local relativity principle or like the light principle are consequences of the strong equivalence principle, which like I take this question to be answering in the place of classical field theories. Can we say something about quantum field theory, or sort of semi-classical gravity, I guess.
Or even just basic like manipulating qubits.
I don't know. I haven't done it yet. But I feel like having a handle on how this works in the classical field theory step was like the first step towards answering the quantum questions. So I don't know. I take this to be progress.
Thank you.
Okay, thank you. So, thank you, Eleanor.
Thanks.
See you all next week for Mike Schneider's talk.